You're welcome to N.H.S tutorial. My name is Mr. James Godwin, a boy from Kenya. I'll be taking you today on the topic electrolysis in chemistry. Now, what does the word electrolysis implies? As from the name, as it was formed. Electro means the introduction of electricity into a compound. And lysis means splitting. In science, anyway you see the word lysis, it means breaking, splitting. So electrolysis will simply imply the introduction of electricity or electric current into a compound that leads to the splitting of that compound into its component ions. That's the word. So we simply define electrolysis as the introduction of electricity into a compound that leads ultimately to the splitting of the compound into its components ions. Components ions. Now, if you ask me, what are ions? Ions are elements that carries electric charge. This electric charge can be positive or negative. Or you can simply put, in some other words, ions are radicals or elements that carries electric charge. This charge can either be positive or negative. These charges can either be positive. If they are positive, the ion is called a cation, e.g. sodium ion, potassium ion, zinc 2 ion, aluminium ion. Or negative. If the charge is a negative ion, it is called, if the charge is negative, it is called an anion. E.g. chloride ion, hydroxyl ion, SO4 2- ion, etc. Now, having introduced electrolysis to you, next I'd like us to be familiar with some terminologies that will be used to describe electrolysis. Please stay tuned to N.H.S tutorial channel. Let me quickly list the terms used in describing electrolysis. Terms used in describing electrolysis. Terms used in describing electrolysis. will see things like, number one, electrodes or electrolyte. Okay, let's start with the word electrolyte. Number two, let's look at the word electrode. Okay, now what are electrolytes? Electrolytes are compounds, okay? The compounds that undergo that splitting, that is being disintegrated into its component ions during the process of electrolysis is what we refer to as electrolytes. So, electrolytes, like we say, are the compounds that are being splitted into its component ions during electrolysis. E.g., you can have something like aqueous sodium chloride. The sodium will be split into sodium ion and chloride ion. You can have something like H2SO4. H2SO4 has its component, so it's split into hydrogen, 2 moles of hydrogen ions, and SO4 2 minus ions. So these are 2 different compounds that were subjected to electrolysis. Okay? First, the compounds are split into these ions. They are component ions. So the compounds undergoes ionization. That's being dissolved in water to produce its component ions. Okay? Then next on the list we are looking at electrodes. Electrodes are those poles that are deep into the electrolyte, through which the electric current, the electricity from the external source is passed into the solution. So the electrodes are those metallic poles, or those poles that conduct electricity that are deep into the electrolyte, through which electricity from the external source, from the DC supply, gets into the electrolytes. Okay? We have the positive electrode called the anode, and we have the negative electrode. So the electrode itself, is split into, we have 2 electrodes. We have the positive one called the anode, and that's the positive electrode. The negative one called the cathode. So during electrolysis, cations are positive charge ions, so they are attracted to the cathode, being negatively charged pole. The anions, which are negative charge ions, are attracted to the what? Anode, being positively charged, as a result of the law of electrostatics. It's a result of the law of electrostatics. We say unlike charges attract, while like charges what? Repels. Okay? You might sometimes come across a question asking you what is the difference between electrolyte and a conductor. Differences between electrolytes and a metallic conductor. Now let's just try to make out some of these differences. On this part, we will write electrolyte, and on the other, we write conductor. Now, one of the fundamental differences, electrolyte is being splitted during the process when it's trying to conduct electricity. It's splitted into its component ions. Whereas metallic conductors like the wires are not splitted in the course of conducting electricity. So metallic conductors remain intact while electrolyte are splitted in the course of electrolysis. That's one. So electrolyte is splitted into its component ions during the course of electrolysis, while metallic conductors remains intact all through the process of conducting electricity. Secondly, we can infer we can just simply infer that electrolyte can undergo both oxidation and reduction, but nothing of such happens to a metallic conductor. So electrolyte can undergo both reduction and oxidation, but nothing of such happens to a conductor. Okay, so that will lead us. I would like to discuss with you the facts, the laws that governs electrolysis. There are two laws that governs electrolysis. The laws that govern electrolysis. There are two laws that governs electrolysis. Faraday's first law of electrolysis and Faraday's second law of electrolysis. Laws of electrolysis. Say there are two laws that governs electrolysis. One, Faraday's first law of electrolysis, and two, Faraday's second law of electrolysis. Now, why Faraday's first law compares the mass of an element discharge being proportional to the quantity of electricity that is allowed to flow through the electrolytes. The second law tries to compare the relative amounts of moles of an element deposited and the charge on the ions of the element. Let's take a look at the Faraday's first law and how it affects the mass of an element deposited during the course of electrolysis. Faraday's first law of electrolysis states that the mass of an element M deposited during the course of an electrolysis is directly proportional to the quantity of electricity that flows through the electrolytes. That is, passing through the electrolyte. That is to say that M mathematically is directly proportional to what? Q, mass of the element deposited, directly proportional to the quantity of electricity, Q, passing through the electrolyte. And from there you introduce a constant called your electrochemical equivalent, which is represented by the symbol Z. So M will be equal to ZQ. If you try to make Z the subject of the formula, you have that Z is equal to M over Q, which means by implication, if we have this proportion, it means we can also have that Z is equal to M1 over Q1, which is equal to what? M2 over what? Q2. This can be deployed to solve equations that pertains to Faraday's first law. Now, to make it more convenient and more appropriate for the solving of the equation that pertains to Faraday's first law, we can say, for instance, remember that charge is equal to quantity of electricity is equal to current as current times time. Time in seconds. Time in seconds. Current is I and time is what? T. So we can use, in place of Q, we can say IT. And then to further modify this formula to suit its applications once and for all when you're solving an equation, instead of using first principle by comparison, can use further modify this equation. It becomes, let's look at it together. We can then make one of these standard. If, for instance, if a metal, which is having the oxidation number of +1, has to gain n number of electrons, okay, to be deposited as metallic solid. The n number of electrons there represents the numbers of Faradays, and the numbers of Faradays, that's n electron, represent numbers of what? Faradays. And numbers of Faradays is that N times 96500 coulombs. This is what will be used. So we will say N Faraday. So or we can simply say NF. NF in place of NQ. And the NQ or NF represent what? Q. So if M1 is presenting the standard, then NF, that is if M1 represent the standard mass of the elements, let's say capital M, then in place of that, it can become, the equation can become modified, and then our Z will imply Z will be equal to capital M. So Z will be equal to capital M all over. For standard mass, we use standard quantity of electricity. So capital N all over NF is equal to M2, which is M2 now representing small n, the amount of mass an element with quantity of electricity Q2 can deposit. Now let's use Q2 to represent IT. So in this case, we can say our IT represents Q2 and our M2 is representing molar mass. Oh, sorry. It's representing N, not molar mass. M1 represents molar mass. M2 is presenting just N, which is the given mass that will be deposited. Okay, so N, small n, all over what? IT. In this case, if you are asked to find the given mass of an element that will be deposited when a particular quantity of electricity is allowed to flow through, you can say, making this the subject of the formula, okay, from this equation, we can say that our small n will be equal to MIT all over what? NF. This is more convenient for solving equations that pertains to Faraday's first law. So say Faraday's first law. This is more convenient and very much straightforward. First law. Please stay subscribed to our YouTube channel as we take you more deeper into solving questions as regards to electrolysis. Now let's look at an example of questions that will need this Faraday's first law to be able to analyze and solve. Let's say the question is asked, say calculate example 1, calculates the mass of calcium. The mass of calcium deposited when a calcium salt is electrolyzed. By passing a current of 3 amperes 30 minutes. In brackets, when we're given something like this, that F is equal to 96500 coulombs. Okay, and Ca is equal to 40, as the case will be. Now, these are the only information you need to be able to analyze and solve to be able to know the mass of calcium that will be deposited. That mass of calcium that will be deposited, by looking at the formula, you have been given the molar mass in bracket, molar mass of calcium to be what? 40. Now you need to know the equation for the reaction. Now calcium, okay, all calcium salt, calcium has Ca2 plus as an ion. So they will need to gain 2 electrons to come out as Ca solid. Okay? Ca2 plus to be able to gain what? It needs to gain 2 electrons to come out as Ca solid, as calcium being deposited. Now in that case, by applying this formula, where M is the mass of calcium deposited. So this one is more simplified. M is the mass of calcium deposited. N is the molar mass as given. I is a current as given. T is a time, but this time should be converted to seconds. So let's quickly do that together. Let's convert the time to seconds. T will be equal to 1 hour 30 minutes will be equal to 1 hour in minutes. First of all, convert it to minutes and convert all of them to seconds. 1 hour in minutes is 60 minutes. So 60 minutes plus 30 minutes. All now in minutes. So together we have 90 minutes. So 90 minutes in seconds will be 90 times 60. So 90 times 60, 9 times 6. 9 times 6. That's about 56. 9 times 5 is 45 plus 9. And that's about 54. Okay, 54, yes, that's about 54. That's T is equal to 5400 seconds. Now, this is what we are going to subscribe. We're going to substitute over here. So, our M from that question will now be the molar mass. Molar mass, so times the molar mass of calcium, which is 40. So, 40 times the current. Current here is 3 amperes times the time. Time is 5400 seconds divided by the numbers of charge. Charge is 2. That's 2. So 1 Faraday is equal to 96500. So these zeros take care of these zeros. So when you multiply and divide, you get consequently the mass of the elements deposited. We can quickly do it together. So we can approximate. In chemistry, we always like our answers to be correct to 3 significant figures. So that gives us M is approximately 3.36 grams, correct to 3 SF. Thank you. Okay, this is how to calculate the mass of calcium. The mass of calcium deposited when a calcium salt is electrolyzed by passing a current of 3 amperes and 3 amperes in 1 hour 30 minutes. This is how to run down the calculation. Okay, so following Faraday's first law, okay, we are talking about just one salt. So we follow the Faraday's first law of electrolysis. Now let's take one more example of this. Okay, quickly so that you can master this. Okay, let me just say calculate the mass of zinc deposited when a zinc salt is electrolyzed by passing a current of 5 amperes in 1 hour. 5 amperes in 1 hour. Now you're giving the relative atomic mass of zinc as 64. Okay, so you are going to use this as the relative atomic mass of zinc in that case. Now, following the same principle, now zinc is usually, as a metallic ion, zinc is Zn2+, meaning that it will have to gain 2 electrons to come out as Zn solid from its aqueous solution. Okay, that being the case, we convert the hours to seconds. So our T there will be equal, 1 hour will be equal to, in seconds, will be 60 times 60, which is 3,600 seconds. That's our T. Then the mass of zinc using Faraday's first law. The mass of zinc as mass that will be deposited will be equal to capital M IT all over what? NF. Now to substitute to get the mass of zinc, you have mass of zinc deposited will be equal to molar mass, which is 64 times the current, which is 5 amperes, 5 times the time in seconds, which is 3,600, all over the numbers of moles of electrons needed, which is N, which is 2, times 96500 coulombs. So 2 zeros, take care of these 2 zeros. Okay, thank you. Zn equal to 5.968911 and so on. And in chemistry, preferably your answers 2, 3. The fourth is up to 5 and above. Borrow 1 and add here, so it becomes mass of zinc deposited will be equal to approximately 5.97 grams, correct to 3SF, 3 significant figure. So this is therefore the mass of zinc that is deposited when a zinc salt is being electrolyzed by the passage of 5 amperes in 1 hour. This is the amount in mass of zinc that will be deposited. Okay, next let's look at Faraday's second law. What does it tell us? Faraday's second law of electrolysis. Faraday's second law of electrolysis states that when the same quantity of electricity is passed through solutions of different electrolytes connected in series, the relative numbers of moles N of each of the elements deposited is inversely proportional to the charge on the ions of the elements. So we're talking about Faraday's second law. So this law states that when the same quantity of electricity is allowed to flow through two or more electrolytes or two or more electrolytic cells connected in series. The relative numbers of moles N of each of the elements deposited or discharged is inversely proportional to the ions on each on each of the elements deposited or discharged. So the ions, we're going to represent it as C. Let's say ions as C. That is to say, mathematically, that N, which is representing numbers of moles, is inversely proportional to the what? Charge. So the charge here is what? C, where N represents relative numbers of moles and C represents what? Charge. Now, if we introduce a constant, it becomes our N will be equal to Z all over what? C, where Z represents the constant of proportionality called the electrochemical equivalent. Constant of proportionality. Then, if by virtue of making Z the subject of the formula, then Z will imply N times C, which is NC. So, which means that our Z can be equal to, we are talking about more than one electrolyte. So N1 C1 is equal to N2 C2, which is equal to N3 C3. Now, each of these are representing relative numbers of moles on the first electrolyte and charges on the ions of the element on the first electrolyte, and represent relative numbers of moles of the elements in the second electrolyte and the charge on the ions of the second electrolyte. The same thing. N3 represent relative numbers of moles on the third electrolyte and elements in the third electrolyte, and the relative numbers of relative charge on each of the elements in that electrolyte. So we're talking about the ions, the charge on the ions. Now you should know that N, which is numbers of moles, and numbers of moles, N is given as given mass or reacting mass. Given mass or reacting mass over molar mass. Over what? Molar mass. So given mass or reacting mass over molar mass. So that is given mass, small m, molar mass, capital M. So it's, by the time you use it to replace what we have there, if we are talking about comparing two electrolytes, let's assume we want to compare the first two electrolytes. electrolytic cells, we'll just say M1 all over the molar mass of M, molar mass of that N, times C1 is equal to M2, representing this over, that is this all over its molar mass, times the charge of C2, and so on and so forth. So this can be modified in this form. Okay, we can still compare it to M3, which is all over the molar mass of M3 times its charge C3. Okay, we can see compare. Okay, now let's see a typical questions that pertains to Faraday's second law. Welcome back to Noble's tutorial channel. Let's look at this question that we have to apply Faraday's second law. The question reads on the board. It said a copper and silver voltameter are connected in series. That's the electrolytic cells. They are both connected in series. At the end of a period of time, 5.0 grams of copper was deposited, which means it's deposited at the first electrolytic cell. Calculate the mass of silver deposited at the same time in the second electrolytic cell. Now, for you to do that, you have to apply, remember the caution. Faraday's second law are there must be two or more electrolytic cells connected in series. That's a condition that tells you which law to apply. The law to apply is Faraday's second law of electrolysis. That states that, now in this case, you're going to use M for copper, MCU all over molar mass of NCU times the charge, we'll call it CCU, is equal to that of silver, MAG, all over molar mass, capital MAG, times the charge of silver, CAG. Now, we should remember this is what the Faraday's second law of electrolysis states. Now, we are comparing two electrolytic cells, so I constrict it to just these two compartments. Now, you remember that copper, for 1 mole of copper to be deposited, copper is Cu2 plus. Are you there? Copper is Cu2 plus. It will have to gain 2 electrons to come out as Cu solid. So from here we are going to get the charge. Very important. So that of silver is Ag plus. Silver will need to gain 1 electron to come out as Ag solid. So from these equations, you can see the ions we have listed it down. From this equation, you can see that CAg is 1 by the charge of silver, and CCU for copper will be what? 2. Now, when we are introducing it, so we are looking for the mass of silver deposited, which is this. Now, you are given the molar mass of silver, which is 108, and the molar or relative atomic mass of copper, which is 63.5. Now, the given mass of copper deposited is 5. So now we're going to substitute to go this way. Then here is 5.0 gram all over 5.0 gram all over molar mass of copper is 63.5 relative atomic mass times the charge of copper, which is CCU, which is 2, is equal to given mass. We don't know the given mass of silver that is deposited. Molar mass is given as 108 times the charge, which is 1. So we simply try to make MAG the subject of the formula. Now, by doing so, quickly, 1 times MAG is MAG. So we have MAG all over 108 is equal to Now this side, 2 times 5, that is 10. So we have 10.0 gram all over 63.5. Simply cross multiply, and that will imply MAG times, you cross multiply, MAG times 63.5 is equal to, that's 10.0 gram times 108. So dividing both sides by 63.5. So 63.5. This cancel out here. So what we just need to do, we'll multiply 10 times 108, then divide by 63.5. That will give us the mass of silver that will be deposited. Correct to 3 significant figures, standard for report. That will be 1, 2. This one is not up to. This is the third one. This is not up to anything. So it ends at 17.0. This third one is not up to. 17.0 gram, correct to 3 SF. That is the mass of silver that will be deposited in the second electrolytic cell. It's as simple as that. Just make sure you don't break any mathematical principle. And make sure you are able to get the charges from the half equations on both electrolytic cells or voltammeter cells. Once you're able to get that, then you are set. You substitute, make the change subject of the formula, and then do your calculations, and there you are. Okay, let's take down another question. Now, looking at what we have at the board, is it a silver and copper electrolytic cells are connected in series. If 43.5 grams of silver is deposited in the first electrolytic cell, calculate the mass of copper that will be deposited in the second electrolytic cell. Remember, the condition is that the 2 electrolytic cells are connected in series, which is the condition to enable us apply the second law of electrolysis. Okay. Now remember, first you write the 2/2 equation. The 2/2 equation, Ag is +1 all the time. It will have to gain 1 electron to come out as Ag solid from its aqueous solution. Whereas copper is Cu2 plus. Okay, copper 2 salt is used. It has to gain 2 electrons, most stable form, to come out as Cu solid. Now, which means that from here, our CAG is equal to 1 and our CU is equal to 2 by their charges. Now, using Faraday's second law, where we have our MAG, that's MAG all over molar mass of MAG times CAG is equal to capital M, okay, small m Cu all over capital M Cu times CCU. Okay, when we do that by substituting, the given mass of silver given up here is 43.5 grams. Molar mass, relative molecular mass of silver is 108, is equal to, okay, times the charge of silver from the equation is 1, and then is equal to the mass, the given mass of copper is what we are looking for, which is a mass of copper that will be deposited by the same quantity of electricity that is allowed to flow through those electrolytic cell connected in series. So I have MCU, which we're going to make the subject formula. All over 63.5 times CCU is equal to 2. So as quickly as we can, we'll make MCU the subject of that formula. And that will give us MCU times 2. So we have that's 2 MCU all over 63.5 is equal to 1 times this, that is 43.5 grams all over 108. We cross multiply, okay? That becomes 2 times this and this. So this is multiplying this and this is cross multiplying this side. So we have 2 MCU times 108 is equal to 63.5 grams. Okay, 63.5 times 43.5 grams. So here we divide both sides. In order to make just MCU the subject, divide both sides like 2 times 108. So 2 times 108. Now, if you are dividing, you can do it like this. If your calculator is not that advanced, or you do it like this, multiply 63.5 times 43.5, then you can divide what you have by 2. So we have 12.788. 12.788. That's correct. Now, we always like in standard reporting it in 3 significant figures. So our N from this calculation, our M will give us MCU will be approximately 12.8 grams. This is the third one, borrow one from here is up to, and add it becomes 8. Correct to 3 significant figures. That is as simple as we can keep it to calculate for Faraday's second law. Remember the conditions that the same quantity of electricity is allowed to flow through them, and they must be connected in what? Series. And it must be comparing 2 electrolytic cells or 2 voltameters that are connected in series. That way, that nobody needs to suggest to you that you need to apply Faraday's second law. Those indicators tells you which particular law you ought to apply. Now next, I need to just talk about, in summary, the applications of electrolysis. Electrolysis is of vital importance in chemistry and in industries. Now, electrolysis helps us to be able to manufacture important chemicals that are so reactive and isolate elements that are so reactive, like sodium, like potassium, like aluminium, like important compounds like potassium thiochloride 5. These compounds are on a normal basis cannot be isolated from normal chemical reactions. We can only use by electrolytic reduction to be able to isolate them from their compounds. And that's just one application. Number 2, electrolysis is applied in electroplating of metals to prevent metal from rusting, like steel, like iron is electroplated with steel, or other metals can be electroplated with metal that does not corrode. That prevents corrosion. Okay? And number 3, electrolysis can be applied in coating of objects or like jewelries. For instance, you want to coat a silver jewelry with a metallic gold. Then you have to place the metallic gold at the anode to be deposited on the jewelry of the metallic silver at the cathode, and that is still a process of electrolysis. So electrolysis, my dear, is very important, an essential tool, an essential use, that's essential use in chemistry. It cut across chemistry and physics, and even cut across a field in medical sciences, because you have to apply dialysis and for drilling of dialysis for draining of kidneys that are defective. It is still the application processes. Okay, very important. Thank you for watching out Noble tutorial. Please stay connected for more videos like this and remain blessed. God bless you.